God. I welcome all of you to the class. In the previous class, we were talking about the two-dimensional state of stress. And in case of a two-dimensional state of stress, I told you students that a two-dimensional stress element is represented in the form of a cubical stress element. Okay. And we represent the normal stress along x-axis as sigma x. We represent the normal stress on the element along y-axis as sigma y. And we also represent the shear stress on this face as tau xy and shear stress on this face as tau yx. Tau yx, okay? This is tau yx. Now, this condition of stress is also known as the plane stress condition. This is something important which I had to share today with you. This is called the plane stress condition. Now, what do we understand by the plane stress condition? Plane stress condition means that we assume that there are stresses along x-axis, normal stress along x-axis, there is normal stress along y-axis, there are shear stresses along x-axis and shear stresses along y-axis, but there is no normal stress along z-axis, and all the components of shear stresses along z-axis, tau xz, tau yz, are all equal 0. There is no component of stress along x-axis, okay? So we call this condition of stress as the plane stress condition. This is something important that we often encounter in while we deal with the structural elements or the machine components, okay? So we take a stress element like this. We essentially take a stress element, okay? We say this is the x component, or let's suppose this is delta x, this is delta y, this is delta x, this is delta y, okay? This is, and as far as delta z is concerned, this is almost equal 0, okay? That is the thickness of the element is very small, and there is no component of normal stress acting along z-axis, okay? There is no component of normal stress acting along z-axis, nor we have any shear stresses acting along the z-axis. Such a condition of stress is called the plane stress condition. You can see the plane stress condition as I was talking in the previous class, I had given an example of plane stress condition as I had given the example of plane stress condition in the previous class as this one, okay? If you look here, an element has been taken here, okay? As far as this element is concerned, this element belongs to the fuselage of an aircraft. It belongs to the fuselage of an aircraft, okay? Such that the element that is being extracted, its thickness is assumed to be very small. Its thickness is approximated to 0, okay? I hope that we can simulate or we can do some experiments on the plane stress condition in the lab, where we'll get, I hope it will be done. So you'll be having component of stress along x-axis. Why? Because you have the entire fuselage filled with the high pressure air, okay? Why I'm saying high pressure air, I was telling you last time, because outside when the aircraft is flying at, say for example, 32,000 feet, okay, at that time, at that height, the outer atmospheric pressure is very small, okay? But humans have to survive. For their survival, the internal pressure is kept at equal to atmospheric pressure. That is what humans require for normal breathing process, okay? So internal pressure inside the fuselage, inside the aircraft is 1 atmospheric pressure, okay? But outside it's less than 1 atm, okay? So that means the internal pressure is greater than the external pressure or outer pressure, okay? That's why we say this is high, internal pressure is high, okay? So that pressure will try to increase the length of this aircraft. So essentially, if you look at this element will be stressed in this direction. The tendency of the gas is to cause an extension in the length, okay? At the same time, It also tries to bulge it out. Okay, it tries to set the bulging in it, it tries to increase the diameter, so you will be having stresses in this direction. But look at the thickness of this element. The thickness of this element is very, very small. Okay, by saying the thickness of this element is very, very small, internal pressure will also tend to move the element in this direction. But since the thickness of the element is very, very small, and on that very face, very small or negligible amount of stress will be acting. That is, I mean to say, in this direction, the stress acting sigma z is almost equal to 0. So whenever you are having the state of stress where you have stresses acting along x-axis and y-axis, whether normal or shear, you have to treat that condition as a plane stress condition. Now, in the previous class, I was telling you that how do the stresses rotate? As you have drawn the Mohr circle now, you are fully acquainted with the concept of the Mohr circle. Now we have to do a little bit of mathematical concepts. We have to do a little bit of mathematics to understand how we actually draw the Mohr circle. What is the mathematics behind the Mohr circle construction? That's very important, and that's quite easy. Okay, so we will be having one more method of doing the stress transformation. If you have a two-dimensional state of stress, if you are being asked what is the state of stress on a plane if the element is rotated by angle theta, okay, then we can easily do all these things. The reason is that we know how to construct the Mohr circle, and from Mohr circle we can look at the stress distribution on any element, whatever be the sense of rotation. But let's today start one more important concept, that what is the fundamental basis of this Mohr circle? I mean to say that how does the Mohr circle work? Okay, so that is what we call as what the chapter states as the general equations of plane stress transformation. Okay, general equations of plane stress transformation means, let's talk about the general equations. Okay, the mathematical equations, let's derive them such that if we substitute the given value of sigma x, sigma y, tau xy, theta in those equations, we'll get the value of the state of stress on a given plane. Okay, so first of all, how the dialogue states, how the chapter starts, it starts with a given state of stress. Okay, so let's suppose we have a state of stress, we have a two-dimensional state of stress, we have stress acting along x-axis, we have stress acting along y-axis, and on this element we have shear stresses acting as well. Okay, so on an element, we have normal stress acting, we have stress acting along x-axis, we have stress acting along y-axis. We do have the normal or the shear stresses acting on the element. Okay, so we have what we call as we have the normal stress acting along x-axis, we have the normal stress acting along y-axis. We do have what we call as the shear stresses acting on this on the plane. Now the question is, as we have done in the Mohr circle construction, let's suppose that this element is rotated in anti-clockwise direction by an angle theta. So we get this. Okay, so as this element, let me call this as element A, as element A is rotated about its center, okay, in an anti-clockwise direction by angle theta, so we get element B. Now the question is, if on this element along the normal axis you had normal stress equal to sigma x, you had stress acting along y-axis as sigma y, and shear stresses acting on the element is tau xy. Now the question is, now what will be the stress acting on the element in this direction, what we call as sigma x prime. Okay, this is now x prime axis, and this is our x-axis. So if you just see, we had initially the x-axis like this, and this was our y-axis. So this was the origin. Okay, let's rotate the system about the origin. So x-axis will be x prime, and y-axis will go to the y prime. Okay, and it has been rotated by an angle. It has been rotated by an angle theta. Okay, now this is our new x-axis, x prime, and our new y-axis is y prime. Now, if you initially had the state of stress on an element like this, along x-axis sigma x, along y-axis sigma y, and shear stresses you had tau xy. Now my question is, if this element is rotated upon an axis passing through its center so that we obtain the element B, what will be the state of stress on this element? Now that is the question. Okay, what is the state of stress on element B? That is, how much is the stress acting along this axis? How much is the stress acting along? How much is the stress acting along this axis, y prime axis, and what will happen to the shear stresses? Okay, that's what we were actually trying to do when we talked about the Mohr circle. In order to do that, look how your book starts. I will be just repeating the concepts illustrated by the books so that it becomes easy for you. This is what all the books on the solid mechanics have done in order to understand the state of stress on different elements. Okay. Now what has been done? Look on the element. This is our element previously, right? This element is like, okay, this is the state of stress on this element. You had sigma x, sigma y, and tau xy. This is our x-axis, this is y-axis. What we are doing, we are taking a wedge. Look at the wedge that has been taken. A wedge element has been taken. Okay, a wedge has been drawn on this here. Okay, if you tend to complete this wedge, it will be essentially like this. If you tend to complete this wedge, it will be like this. Okay, so this wedge that is being introduced here, okay, if you complete this wedge essentially is a part of an element which has been obtained by rotating this element by some angle, okay, that's what we call as an angle theta. Okay, it has been rotated by some angle, that's what we call as an angle theta. So the analysis that is being done, it is usually done on a small element, on a wedge element. Okay, that's like this. This is something that we need to understand, why the wedge element has been extracted on an inclined plane. So what is being done? So if you complete this wedge, you just try to see this wedge is nothing. It is part of some element. Okay, it's part of some element. Okay, this wedge is a part of element. This wedge is a part of an element. Okay, it is in fact I can say it is side of an element. Okay, this is side of an element. Okay, which is this element, pink element, which has been rotated, which has been obtained by rotating element A by angle theta. Okay, now if we can do our analysis, or I can say now this is my x-axis. Where is my x-axis? This is my new axis. This is sigma, I say x prime axis. Okay, x prime axis. And if I, this is my y-axis, new y-axis. This is y prime axis. Okay, this is my new axis. So stress acting along this axis will be sigma x prime, and stress acting along this axis will be sigma y prime. And shear stress acting on this plane will be tau x prime y prime. Same will be the case here. I have to find now, I have to find what is sigma x prime, what is the normal stress acting on the element. I have to find what is the sigma y prime, and I do have to find the value of tau x prime and y prime. Okay, so how the analysis has been done? Out of the element, out of the given element, a wedge element has been taken out, that is here. Okay, now on this element, an axis in this direction is x-axis, that is x prime axis, and an axis in this direction will be our y-axis, that is y prime axis. Okay, this is our angle, small angle theta, by which the axes have been rotated. Now, if we assume the area of this inclined area or the wedge area is delta A, okay, then we can simply write that this face will have the area equal to delta A cos theta, and this face, the bottom face, will have the area equal to delta A sin theta. This is quite easy to visualize because we know cos theta is equal to base. Let me write this as base area AB divided by hypotenuse, that is delta A. Therefore, the area of the base AB will come out equal delta A cos of theta. Okay, that's what has been written here, delta A cos theta. Similarly, the area of this side will be equal delta A sin theta. Okay, now let's do a very important step. Since whether you have an element like this, you have a simple element like this, a square element, or this wedge element, okay, or a portion of this element, or this wedge element like this, or this wedge, which is a portion of a big element, it has to be essentially in, the system has to be essentially in equilibrium. Okay, how the system will be in equilibrium? When the summation of forces will be equal 0. Now look at the force diagram. Look at the force diagram. Now, first of all, we obtained from this element, we obtained this element, and now we'll do the force balance. Okay, so along x-axis, along this new axis, the stress acting is sigma x prime. How much will be the force acting along this axis then? It will be, I mean to say is, let me, along this axis, The stress acting along, this is my x prime axis. The stress acting is sigma x prime, which I had to find. Therefore, how much will be the force? Stress multiplied by area, that is delta A. This will be the normal force acting on this area. Okay. Apart from this, on this face, we are having the shear stress acting tau x prime y prime. How much will be the shear force multiplied by the corresponding area? That is delta A. That has been written here. Okay. So this is very important. Similarly, on this face, how much is the area of this face? Area of this face is delta A cos theta. Area is there. How much is the stress acting along this direction or in this direction? Okay, it is sigma x. Therefore, how much will be the force acting on this face? That will be sigma x delta A cos theta. Similarly, the normal stress acting on this face, you have normal stress acting sigma y. Okay, on this face, sigma y. Okay, on the bottom face, you have normal stress acting in downward direction as sigma y. Okay, how much will be the force? That is sigma y delta A sine of theta. Stress multiplied by the corresponding area. Are you getting me or not? Apart from this, on this face, we are having shear stress acting. This is tau xy. How much will be the force in this direction? It will be tau xy multiplied by this area, that is delta A cos theta. That is here, tau xy delta A cos theta. In the same way, on this face, on the bottom surface of this wedge, you are having shear stress acting as tau xy. How much will be the force? Tau xy multiplied by the area of this face. That is tau xy into delta A sine theta. Okay, so it means the overall stress element can be now written like this. Let me redraw this. The overall stress element can therefore be written as, the overall stress element can therefore be written as, we have a stress element you have overall stress element can therefore be written as, we'll be having, let me draw it with a black pen. Okay, let me draw it like this. We have a stress element like this. Wedge element is like this. Okay. On this face, we have stress acting. Force acting is sigma x prime multiplied by delta A. Okay. And on this face, the normal stress acting is sigma x into delta A cos theta. And on this face, the stress acting is sigma y delta A sine theta. Okay. And we have the forces acting in this direction as shear stress acting in this direction is, this shear stress is tau xy delta A cos theta, and shear stress on this face of the wedge is equal tau xy delta A sine theta. Okay, this is done, this is done, this is done. Okay, apart from this, we will be having shear stress on this face as, that is, the shear stress on this face is tau x prime y prime, and the corresponding area is delta A. Okay, we will draw the axis. This was our initial x-axis. Okay, this axis is a new x-axis which has been rotated by taking angle theta in the anti-clockwise direction. Okay, now what we do? Now we will be performing a very, very important step, that is the resolution of the forces. We write now, for the equilibrium purpose, this is x-axis, this is the new x-axis, that is x prime. We write this equation for the equilibrium. summation of all the forces along the new x prime axis should be equal to 0. Summation of all the forces along the new x prime axis should be equal to 0. So take the components of all the forces along this x prime direction. Okay. So what are the components of forces acting along this x prime direction? First of all, we have the force sigma x prime delta A. So we are writing sigma x prime delta A. This is positive because this is along positive x axis. Okay. In the same way, we have one more component. Okay, if you look at this component of the force, that is okay, that is um, okay, let me first take this only sigma x prime. Then we have okay, I have done this. The sigma x prime delta A is a force acting along x prime that I have written, that is here. Okay, sigma x prime delta A is here. What is the next force acting along x prime axis? The next force is taken as tau xy delta A sine theta. If you look at your tau xy delta A sine theta, that is this force. Okay. So this force essentially is acting along negative x-axis. That is this force. I will draw it here. This is our sigma x. This is our x prime axis. Our tau xy delta A sine theta is acting along this direction. Okay. This is tau xy delta A sine theta. Okay. And this angle between them is, this angle is theta. Fine, because you can draw this force parallel to itself. By taking a force parallel to itself from mechanics, the magnitude, the nature of the force does not change. Now we have to see how much is the component of this force tau xy delta A sine theta along x prime. That will be equal tau xy delta A sine theta. This is the force. Now we have to calculate its component along x prime. That will be equal to cos of this angle, that is pi minus theta. That is cos of pi minus theta. Okay, pi minus theta is the angle in second quadrant. That will be minus tau xy delta A sine theta cos theta. Okay, but minus, that is what has been written here. Okay, this is the second term here. First term we know, the second term here represents the component of tau xy delta A sine theta along x prime direction. Okay, now take the third term. The third term that has been written is, this. It is sigma xy delta A sine theta. Sigma y, it is sigma y, okay, delta A sine theta. That is this component, this force. So this force is acting along downward direction. So you have the force acting in downward direction. It is sigma y delta A sine theta. Okay, and this is our x prime. This is x prime, and this angle is given to us as angle theta. Okay, now what will be the component of this force along x prime? That will be cos of this total angle, cos of 90 plus theta. So the component will be sigma y delta A sine theta multiplied by cos of 90 plus theta, cos of pi by 2 plus theta. Okay, cos of pi by 2 plus theta is sine theta. Okay, it is in second quadrant. In second quadrant, sine is positive. Okay, so in the second quadrant it is positive, but this force is acting downward direction, therefore it will be taken as negative. Okay, sorry, cos of pi by 2 plus theta is minus sine theta. Okay, cos of pi by 2 plus theta is minus sine theta. Okay, therefore it will be sigma y delta A sine theta into sine theta, but minus. That's our second term here. Okay, this is our third term. Okay, so we know what first term represents, what second term represents, and now what third term represents. Now let's see the next two terms. If you look at the next two terms, the next two terms represent the component of force along. The next two terms represent the component of force along. Now we have tau xy delta A cos theta. This is the tau xy delta A cos theta. Okay. Now tau xy delta A cos theta is in this direction. Your x prime is in this direction. Okay. This angle between them is theta. You have to find the component of tau xy delta A cos theta along x prime. If you look at this this force will have the same component as you had sigma y delta a sine theta, because sigma a delta y sine theta was also acting in the same direction. Therefore, its component along x prime will be tau xy delta a cos theta into sine theta. Okay, that is here, and negative because we know how it is. Okay, because this force, this force and this force, they are acting in the same direction. Their angle with x prime is theta. Okay, so the last term that is there is sigma x delta a cos theta. Where is our sigma x delta a cos theta? It is here. Sigma x delta a cos theta is this term. So this force is acting along, this force is acting along this direction. So this is your sigma x delta a cos theta. Okay, and our x prime is in this direction. This is our x prime, such that this angle between them is theta. Therefore, how much will be the component? That is pi cos of pi minus theta. So it will be sigma x delta a cos theta multiplied by cos of pi minus theta. Cos of pi minus theta is minus cos theta. Therefore, the component will be sigma x delta a cos theta into cos theta, but minus. Okay, that's your last term here. Okay, and summation of all these you put equal 0 before the equilibrium purpose. When we do it, so when you solve it, you get this equation. Please get this equation yourself. You get, this is a very important equation. You get sigma x prime is equal to sigma x cos square theta plus sigma y sine square theta plus tau xy multiplied by, this is 2 sine theta cos theta, that will be sine 2 theta. Okay, now what does this formula tell you? If you have a stress element initially, you are given the value of sigma x, you are given the value of sigma y, you are also given the value of tau xy. Now you are asked that the element is rotated by an angle theta equal to, say for example, 30 degree. What is sigma x prime? You can easily calculate. You know sigma x, you know theta, you know sigma y, you know tau xy, you know theta. Therefore, from this formula, you can calculate the value of sigma x prime. Okay. You have any questions?